The topic which I'm going to discuss is diagonalization of a matrix. It is a process of reduction of matrix A to a diagonal form D. If A is related to D by a similarity transformation such that P inverse AP is equal to D, then A is reduced to the diagonal matrix through the model matrix P. So let us have some important notes about the diagonalization. The matrix P which diagonalizes A is called model matrix of A. So the model matrix is formed by grouping the eigenvectors of A into a square matrix. The resulting diagonal matrix D is called the spectral matrix of A. The spectral matrix has the eigenvalues of A as its diagonal elements. So the transformation of matrix A to P inverse AP is called the similarity transformation. So let's establish the result by considering a third order square matrix. So here I have one property regarding the diagonalization of a square matrix. That is, if A is a square matrix of order n having n linearly independent eigenvectors, then there exists an nth order square matrix P such that P inverse AP is a diagonal matrix. So let us establish this result by considering a third order square matrix. Let A be a third order square matrix having eigenvalues lambda 1, lambda 2, lambda 3 and the corresponding eigenvectors x1, x2, x3. So firstly let us form the model matrix P. P is equal to x1, x2, x3 means the model matrix P contains the eigenvectors in columns. Now let us compute AP. AP gives A times the matrix P, that is x1, x2, x3, so which can be taken as ax1, ax2, ax3, since ax is equal to lambda x, so this is equivalent to lambda 1 x1, lambda 2 x2, lambda 3 x3, or which can be written as lambda 1 x1, lambda 2 x2, lambda 3 x3, lambda 1 y1, lambda 2 y2, lambda 3 y3, lambda 1 z1, lambda 2 z2, lambda 3 z3. So this is a product of A into P, so which can be written as x1, x2, x3, y1, y2, y3, z1, z2, z3 into lambda 1 0 0 0 lambda 2 0 0 0 lambda 3. So that is the matrix AP, the product AP will be equivalent to the product P into D, where D is the diagonal matrix. So which is represented by D is equal to lambda 1 0 0 0 lambda 2 0 0 0 lambda 3. Now operating P inverse, that is pre-multiplying by P inverse, so we get the similarity transformation as P inverse AP is equal to D. So hence P inverse AP is a diagonal matrix having the eigenvalues of A lambda 1, lambda 2, lambda 3 in its principal diagonal. So therefore we say that the matrix P diagonalizes A where P is constituted by the eigenvectors of A. So P is called the model matrix. So we can reduce or we can diagonalize the matrix A to D through the similarity transformation, that is P inverse AP. And also we can compute the powers of a square matrix if A is reduced to the diagonal matrix. See, so here T is equal to P inverse AP, then D square is equal to P inverse A square P. So we can establish the relation to compute the powers of A through D is equal to P inverse AP. So that is A square is equal to P D square P inverse, just by pre-multiplying by P and post-multiplying by P inverse to the relation D square is equal to P inverse A square P, which gives A square is equal to P D square P inverse. So this is the relation from which we can compute the powers of a square matrix when A is reduced to the diagonal matrix. So in general, it is given by A power n is equal to P D power n P inverse, where D power n is equal to all the diagonal elements takes the power n. So this is according to the property of eigen values. So D power n is equal to lambda 1 to the power n 0 0 0 lambda 2 to the power n 0 0 0 lambda 3 to the power n. So directly we can write. So if you want to compute, or if you want to find the powers of a square matrix, then we can use this relation, that is A power n is equal to P D power n P inverse. If you want to compute the powers of a diagonal matrix, we can consider this relation. D square is equal to P inverse A square P. In general, D power n is equal to P inverse A power n P. Next, moving on to the problems. Before the examples, here I have the working procedure for diagonalization of a square matrix. Let A is a square matrix of order 3. We want to diagonalize the matrix A through the similarity transformation P inverse AP. So firstly, we have to find the eigenvalues of the given matrix. Then we have to compute the corresponding eigenvectors lambda 1, x1, x2 and x3. Then we have to form the model matrix P. P is equal to x1, x2, x3. So which consists of the eigenvectors in columns. Then we have to compute its P inverse, that is P inverse is equal to 1 by determinant of P times the transpose of cofactor matrix, which we call it as the adjoint of P. So finally we have to compute P inverse AP, which is equal to D. Then we say that the matrix A is diagonalized. So let us consider some examples. The first example, reduce the matrix A is equal to -1 to 2 minus 1 to the diagonal form, hence find A power 6. So in the first example, we have to reduce the matrix A to diagonal form, and then we have to compute the powers of A. So the powers of A is A power 6. So first let us reduce the given matrix to the diagonal form through the similarity transformation, that is P inverse AP. Let us find first the eigenvalues and eigenvalues and the corresponding eigenvectors in the usual way. Let A determinant of A minus lambda I is equal to 0 be the characteristic equation. Expanding this determinant gives the characteristic equation as lambda square plus 2 lambda minus 3 is equal to 0. Solving, we get the roots lambda is equal to 1 minus 3 are called the eigenvalues. So let us denote the eigenvalues by lambda 1 and lambda 2 to find the corresponding eigenvectors. To find the corresponding eigenvectors, let us form the matrix equation, for which let us consider in general the eigenvector, that is x is equal to xy. So this is an unknown column matrix. Okay. Then the matrix equation is A minus lambda I times x is equal to 0, which gives -1 minus lambda 2 2 minus 1 minus lambda times the matrix x that is xy, which is equal to 0. Denote this matrix equation by 1. So let us solve this matrix equation for lambda 1 is equal to 1 and lambda 2 is equal to minus 3. When lambda 1 is equal to 1, the matrix equation 1 will reduces to minus 1 minus 1 minus 2, 2, 2 minus 2 xy. This gives the equivalent system of equations as, or we can say the linear equations as minus 2x plus 2y is equal to 0, 2x minus 2y is equal to 0. So these two equations yields into a single equation, that is x minus y is equal to 0. So to find x and y, here we can choose one of the unknown to be an arbitrary constant. So here I have chosen x is equal to k1, an arbitrary constant, so that I get y as k1. So therefore the corresponding eigenvector for lambda 1 is equal to 1 is x1 is equal to xy, that is equal to k1 k1 or k1 times 1 1. Here we can choose k1 as 1. Next let us find the eigenvector corresponding to lambda 2 is equal to minus 3. Substituting lambda 2 is equal to minus 3 in the matrix equation 1, we get the equivalent matrix as 2, 2, 2, 2, xy, which is equal to 0. This gives the linear system of equations as 2x plus 2y is equal to 0, 2x plus 2y is equal to 0. These two equations yields into a single equation as x plus y is equal to 0. So to find the unknowns x and y, because here I have only one equation. So to find the unknowns x and y, so I'll choose one of the unknown to be an arbitrary constant. So let x is equal to k2 be an arbitrary constant, so that I get y2 as minus k2. Hence writing the corresponding eigenvector, that is x2 is equal to xy, which is equal to k2 minus k2, which is equal to k2 times 1 minus 1. Now I have got the eigenvectors corresponding to lambda 1 and lambda 2. Now I'll form the model matrix of A, that is P is equal to capital X1, capital X2. So the model matrix is nothing but it contains the eigenvectors in columns. So that is K1, K1, K2 minus K2. I'll choose K1 and K2 to 1. Okay. So that I'll get the model matrix as 1, 1, 1, minus 1. So to diagonalize the given matrix, let us find the inverse of P. Inverse of P is given by the transpose of cofactor matrix divided by determinant of P. Okay. So this gives, so it is a 2 cross 2 matrix. So easily we can find the transpose of cofactor matrix or cofactor matrix, that is just by interchanging the diagonal entries and multiplying the non-diagonal entries by negative sign. So which gives the transpose of the cofactor matrix times 1 by determinant of P. So the value of the determinant is minus 2. So therefore P inverse is equal to 1 by minus 2 times minus 1 minus 1 minus 1 1. Now let us compute P inverse AP. P inverse AP is equal to D. So substituting for P inverse A and P, which will reduce us to D. So D is in the form lambda 1 0 0 lambda 2. So that is equal to 1 0 0 minus 3. So if you compute P inverse AP, you will get this matrix D. Okay. So hence the given matrix A is reduced to the diagonal form. Now let us compute the powers of A. Here we have to compute A power 6. A power 6 is equal to P times D power 6 P inverse. So let us first find d power 6. D power 6 is equal to 1 power 6 0, 0 minus 3 to the power 6, which gives 1 0 0 729. Okay, so P inverse already we have found. Then substituting in this expression for a power 6 is equal to p d power 6 p inverse, which gives 1 by 2 times 1 1 1 minus 1 into 1 0 0 7 29 1 1 1 minus 1, multiplying the matrices, we get the power of A has a matrix in the form 365 minus 364 minus 364 365. So this is how we can compute the powers of A once if we reduce the matrix A to diagonal form. I'll take one more example. So the next example is diagonalize the matrix A is equal to 6 minus 2 2 minus 2 3 minus 1 2 minus 1 3. We have to diagonalize this matrix. So let us compute the eigenvalues and eigenvectors. Let determinant of A minus lambda is equal to 0 to the characteristic equation. That is determinant of 6 minus lambda minus 2 2 minus 2 3 minus lambda minus 1 2 minus 1 3 minus lambda is equal to 0. Expanding this determinant using the cofactor formula with respect to the first row, which reduces to a cubic polynomial cubic equation, that is lambda cube minus 12 lambda square plus 36 lambda minus 32 is equal to 0. Solving, we get the roots, that is 2 2 8, which are called the eigenvalues. So let us denote the each root by lambda 1, lambda 2 and lambda 3 respectively. Let us find out the corresponding eigenvectors. Since we have the repeated repeated eigenvalues 2 2. So let us take lambda 1 is equal to lambda 2 is equal to 2, and we have to get its corresponding eigenvector. Now let us form the matrix equation to compute the eigenvectors. Let x is equal to xyz, that is transpose of xyz. Then the matrix equation be A minus lambda I times x is equal to 0, which implies 6 minus lambda minus 2 2 minus 2 3 minus lambda minus 1 2 minus 1 3 minus lambda times xyz is equal to 0. Now let us substitute the repeated eigenvalue, that is lambda 1 is equal to lambda 2 is equal to 2 in the matrix equation 1. Then 1 will reduce this to 4 minus 2 2 minus 2 1 minus 1 2 minus 1 1 xyz is equal to 0. So before writing the equivalent system of equations, first I will reduce this coefficient matrix through row transformation. The simple operation I can use here is R2 is equal to R2 plus 1 by 2 times R1, R3 is equal to R3 minus 1 by 2 times R1. Then this coefficient matrix will reduce this to 4 minus 2 to 0 0 0. Automatically the two rows will become 0. So it will be easy to find the unknowns. Now writing the equivalent system of equations. So here the two rows are 0. Only I have one unknown row. Hence I'll get only one equation in the form 2x minus y plus z is equal to 0. So let us choose x to be 0. I can choose x is equal to some arbitrary constants, say k1, and also I can choose one more unknown to be an arbitrary constants. Okay. So here I'll, instead of the arbitrary constants k1 and k2, I will take a some arbitrary constants as 0 and 0. Okay, so when x is 0, then this equation will reduces to minus y plus z is equal to 0. Okay, so which gives the ratio y by z is equal to 1 by 1. So therefore y is equal to 1, z is equal to a. Hence the corresponding eigenvector for lambda 1 is equal to 2 is 0, 1, 1. Since it is a repeated eigenvalue, so next I can take the arbitrary constant y2 to be 0, from which I'll get the second set of eigenvector for lambda is equal to same eigenvalue 2 as x2 is equal to minus 1, 0, 2. Next let us get the eigenvector corresponding to lambda is equal to 8. Put lambda is equal to 8 in the matrix equation 1, which reduces to minus 2 minus 2 2, minus 2 minus 5 minus 1, 2 minus 1 minus 5, x y z is equal to 0. Now further let us reduce this coefficient matrix through a row transformation before writing the system of equations, because it will be easy to solve the linear system of equations if we reduce this coefficient matrix further. So here the simple operations I can use is R2 is equal to R2 minus R1, R3 is equal to R3 plus R1. Now operating these two on the coefficient matrix, which reduces to an equivalent matrix minus 2 minus 2 2, 0 minus 3 minus 3, 0 minus 3 minus 3, x y z is equal to 0. And one more operation I can use here, because here I have two rows as similar rows, so easily I can make one of the row as 0. So let us operate R3 is equal to R3 minus R2, then I get the equivalent matrix as minus 2 minus 2 2, 0 minus 3 minus 3, 0 0 0, x y z is equal to 0. Now let us write the equivalent system of equations, which gives minus 2x minus 2y plus 2y is equal to 0, minus 3y minus 3z is equal to 0. Now solving these two equations by rule of cross multiplication. So before RCM I have simplified the equations into x plus y minus z is equal to 0, 0x plus y plus z is equal to 0. Now solving for xyz by RCM gives x by 2 is equal to z by minus 1 is equal to z by 1 is equal to k1. So let us equate these ratios to a common constant, say k1, which gives x is equal to 2k1, z is equal to minus k1 and z is equal to k1. So let us choose k1 to be 1, then the corresponding eigenvector x3 is equal to 2 minus 1, 1. Now I have got all the eigenvectors corresponding to the eigenvalues. Now let us write the model matrix. So the model matrix P is equal to x1 x2 x3, that is equal to 0 1 1. So we have to write all the eigenvectors in columns to form the model matrix. Okay, so that is P is equal to 0 1 1 minus 1 0 2, 2 minus 1 1. Let us find the inverse of P through the formula C transpose by determinant of P. So determinant of P is 6 and the transpose of the cofactor matrix is equal to 2 5 1 minus 2 minus 2 2, 2 minus 1 1. Already we know how to find all the 9 cofactors and how to transpose. So P inverse is equal to 1 by 6 times 2 5 1 minus 2 minus 2 2, 2 minus 1 1. Now P inverse AP is equal to D, that is D is equal to, substituting all the matrices, that is P inverse AP, and simplifying we get the simplified matrix as 2 0 0 0 2 0 0 0 2. See here all the diagonal elements are nothing but the eigen values. So therefore this is equal to D. Hence through this similarity transformation P inverse AP is equal to T, P inverse AP is equal to D. The given matrix A is diagonalize. Here I have few more examples on the diagonalization. Go through the examples.